even the average speed of a male in North America to walk 10 feet, right? We can represent all of these things to completely understand the process. And all that's quite at a high level, actually, from a process point of view. When you start getting into the nitty-gritty detail of engineering, right, you need to be able to program, right? You need to be able to write logic for those controllers that's going to execute tasks on the line. And Siemens led the way in developing a concept around virtually representing the controller. So you can think of it as having a virtual clone of your computer. You're going to write the actual code for it. You're going to run it on the virtual computer. But then what we are capable of doing is then connecting that controller to the virtual line and understanding how the entire thing behaves. So if you recall, in the same way we wanted to understand all the systems within the product, we want to understand all of the systems that are going to impact the production as well before we ever propagate that to actual production. And of course also holistically engineering all of the equipment on the line as well. And in this virtual commissioning process and in the process of engineering here, we're able to capture every bit of automation equipment on the line, from networking and logic controllers to the drives and machining tools on the line as well. And the last thing I want to leave with here is, because we're about to take a step into the real world, if you will, is that at the end of all of these virtual things, the product and the production, you should have an output which allows you to seamlessly publish to the manufacturing floor. And that's exactly what we have here. So we have the complete digital representation of the product. We have a complete digital representation of the process that goes into it. We're able to take electronic work instructions from all of those visualizations and 3D models, and we're able to then publish that down to the manufacturing floor so that you can execute much faster on these product innovations. And as I mentioned, this is where we take it into actual real production. But what we've been able to do is understand as much as possible about the virtual world before, because as one of our previous executives mentioned, who led much of the innovation in acquiring many of these companies within Siemens, there are no consequences in the virtual world. It's a lot cheaper to break things in the virtual world than it is in the physical world. So at this point, we take this process and we publish that down to the manufacturing floor. And now we start to drive new benefits from this as well. So one, we want to be able to optimize our line as best as possible, because it's one thing to create new ways of manufacturing, but we also just want to use the things we already have as best as possible. But because we know everything about production and the product, and we can pull the orders that are coming from the systems on the business side, we can completely optimize production. And then we're able to publish that production down to the human operators on the line. And in fact, so this is of an operator view, and if they were to step into this particular task, then what we're going to see are work instructions that are directly driven by the simulations that we started with at the very beginning. We're not reworking things. We're not tossing things over a wall to somebody. We're seamlessly connecting that data all the way down to the manufacturing floor so that it's useful to that operator in the form of 3D work instructions and other forms. But we can also coordinate those automated tasks as well. So previously, when we talked about automated cells, it were very much isolated cells that did a task, but then at the end of the day, it handed it off to somebody or something, and it did the next task. Now we want to connect everything across all of the automated and the human operators. And just for fun as well, this is actually taken from the point of view of somebody wearing HoloLens goggles. So these augmented reality goggles, right? And so again, those simulations we ran for the human operators, we can drive those down into these new forms of visualization like augmented reality. And now, when we talk about demographic changes, right, only having one expert in a company, they can now put on the goggles, or the new individuals in the company can put on the goggles, they can call that expert and they can get help with the tasks they're doing, or they can use these 3D work instructions to better understand the task that they're supposed to be doing. And of course, even though, as I mentioned, Industry 3.0 is maybe not the way of the past, but many industries are not fully automated yet. So we still are driving towards this concept of a completely, totally integrated automation scheme, right? Connecting from end to end and be able to automate tasks that make sense to automate as best as possible. and allows us to do really interesting things. So I was actually with this particular machine in Germany a few weeks back, but it's way more impressive than it may look. So one, it's sitting on a 2-ton platform, right, that's moving around, and it has this robot, if it was to stand up, is about, I don't know, 15 feet, 18 feet tall, and this robot can go down to like I think it's like 1/100 of a millimeter precision or something like this for these milling processes that it's doing. I mean, it's absolutely incredible, right? But the reason we're able to do these incredible things with this robot that's literally sitting on a moving platform is because we were able to virtually represent and understand what it was going to do. Because for companies like Boeing, if this robot was to do the wrong thing and go 1 millimeter to the right instead of 1 millimeter to the left, then what it'll end up doing is costing them millions of dollars. So again, it's a lot cheaper to break things in the virtual world than it is in the real world. And lastly, we have this idea of digital twin of performance. And this is one of the newest ones that have begun to be propagated in industry, and it's this idea that we can capture data throughout our enterprise and be able to realize different benefits from that, right? So analyzing that using cloud computing and a variety of different engines, analytics engines. And one portion of that is being able to understand what's going on in your production facility. So existing equipment is already probably producing quite a bit of data. There's also new IoT devices that are getting cheaper and easier to implement. And we can capture new data from that as well. And we want to be able to visualize that quickly, use the latest analytics engines that are being produced by Google and academic institutions around the world to be able to drive insight into production. So that instead of let's say, for example, reacting to an issue with a piece of equipment, we could actually predict the issue with that equipment, right? And that's a really fundamental difference for manufacturers because downtime on a line is just absolutely unacceptable today. And on the flip side of that, we're also producing a variety of different smart products. If we think about an airplane, it has the capability to collect a ton of data about the way it's being used as well and the different systems that are driving it. And what we're capable of doing is pulling data from those systems as well, from the product, drive that back to how that product was manufactured, drive that back to how that product was actually being developed in the early stages so we understand, wait, that strange vibratory pattern that's occurring when we put down the wheel on this particular airplane when it's going at 35,000 feet is because of this particular screw that was put in on this particular date that was put in by this particular operator for this design. And that is, it's something that, it's a benefit that we haven't been able to realize at all previous to this and is only capable because of digitalization and this connectedness of all of these systems. And as I mentioned, this really now allows us to have what we call closed-loop manufacturing. It's continuous improvement, right? You're gaining insights from how things are performing, driving those back into your simulation engines and the way you design your product, and then using that to continuously improve the way you produce your products. And this is a really fantastic concept, and it's one, again, that we believe a digital enterprise really has to enable. And in fact, again, just to prove out our confidence a little bit, this is one of our own facilities. So in Hamburg, Germany, it was one of the first ones that we began the digitalization process of internally. In fact, we were doing this digitalization process as we were developing new technologies and acquiring new technologies. And it wasn't a quick process. It's not like 6 months and you're done. You've got a digital enterprise now. This was a 10, 15-year project where we were changing out the technologies. And they're able to do some really fantastic things. So one, they're producing about one product per second, over 1 million of these per month. And these are high-tech electronic components that we sell our customers, because of course we as Siemens also produce. And with those high-tech products, we have over 1,300 variations of that product. And they're still producing one per second. And one thing I do want to key in on here is, so this figure, 9 times the increase in efficiency, that was realized over a period of about 12 years or so. And that realization, though, happened with the exact same number of individuals working in that facility the day they started and the day they ended. So there were roughly 2,400 individuals that work in this facility. Now granted, we've been able to enable them and have them become much more productive in their capacity, but many of those individuals that were working in the facility and prior those unskilled workers or minimally skilled workers, we were able to retrain and work with in new ways in that facility, but it required an extensive process of embracing digitalization from a labor point of view as well. We're also working it's not just aerospace, it's not just discrete manufacturing, it's also, we're working in the footwear industry as well. Because you don't think clothing or footwear has that many opportunities to improve, but what you probably don't realize is your tennis shoes take about 18 months to bring a new product to life. 18 months. You think about how quick trends are happening in fashion and clothing and stuff. 18 months is an unacceptable figure because after 18 months, it's possible that you've completely diverted and nobody is interested in the blue color of sneakers now, just as an example. And so what Adidas is driving towards is this concept of a lot size one. So it's something we call mass customization. It's the idea that I can pump thousands of products through, but every single one of them can be unique. And so what they're doing with their speed factories, they've already built one in Germany and are now building one in Atlanta with a partnership with Siemens, is this idea that you, as a consumer, can walk into your store here in Vancouver, you go to your local Adidas store, you step on some plates. These are not new, right, to measure the way your feet are. In my case, I have flat feet, so I may need a little more arch support, right? And then from there, you decide on what colors you want, what particular form factor, is it for working out, is it for this, that, or the other. And then what they'll do is within 24 or 48 hours, they will have that shoe in production and ship that to your door. And that's something that nobody can do today. And if they are doing it today, if you see any of these mass customized products, it's requiring an immense amount of manpower and actual people sitting down and custom designing things and a lot of rework. It doesn't drive towards the ability to being able to do this with a lot. And we're also working with, I'm quite fond of beer. And if you are as well and you've drank a Modelo in the past year or so, then you're welcome. We helped we helped them expand their brewery in Nava in Mexico to be able to produce roughly 7 billion bottles of beer annually. So they increased their production, they tripled it, right? And that was enabled by highly automated techniques, but digitalization in a different light, because digitalization can realize a variety of different benefits. It can benefit in lot size one, it can benefit in high customized products, but it can also benefit in mass production as well. There's a variety of ways those can be brought to life. Oh, there it goes. I know the last example I want to talk to is a car manufacturer, kind of. They're really rethinking the way we go about and see the car industry, the automotive industry. And so it's a group called Hackrod. And it's some individuals that had a really innovative thought behind how we design and bring new automobiles to life. And so what you're seeing here is a concept of what they're attempting to build, a car called La Bandita, which is a really cool name. And up in the top right-hand corner, that strange spiderweb looking thing is the chassis for that car. And I'm going to play a video by them and let them speak to that, because I think they'll probably do it better justice, though.
Imagine that you could design and build the car of your dreams as easy as playing a video game. The Hackrod digital manufacturing platform is connecting virtual reality with artificial intelligence and advanced manufacturing to make this dream a reality. To prove this out, we started by sketching La Bandita, the car that we wanted, but nobody made. Quickly moving from sketch to full-scale photoreal 3D model in virtual reality. Allowing us to perfect the design and aerodynamics digitally. Moving back into the physical world and connecting with the Internet of Things. We deployed sensors and scanners to capture 50 years of automotive knowledge. harvested massive data sets and used them to teach the artificial intelligence generative design engine what a car experiences. With artificial intelligence and machine learning, we have the power of hundreds of engineers at our fingertips, allowing us to grow optimized engineering solutions for our design requirements. These designs are too complex and expensive for traditional manufacturing. They have to be 3D printed. Hackrod is leading the way in large-scale metal 3D printing.
So Mouse, this is the challenge section. It's that node right there that's really going to make or break this chassis. What we're doing right here, like this is the key.
Right.
If we can get that node, then we can get everything.
We are now ready to print a full-scale car in aluminum. La Bandita is not a concept car. It's a proof of concept of an entirely new way to design and manufacture. And if you can build a car this way, you can build anything.
Again, every video I show seems to have a lot cooler people than me in it. So, no, I'm not disillusioned in thinking that this particular group, Hackrod, is going to be the way every car is produced now or even maybe 50 years from now. But what I do think they're a phenomenal example of is completely rethinking the way that products are brought to life. And with all the technologies that you've seen previously, which I know are quite a lot, many of you are probably like, God, get off the stage already. But with all these products, we're realizing benefits in industry that we've never seen before. But it also means that there are completely new requirements for the type of labor that those enterprises require, the way those enterprises do business. And that requires a completely new way of thinking that I think these Hackrod gentlemen very well epitomize. And the one thing, though, that I haven't really said anything about is myself. So, yeah, I know. Unfortunately, I'm not a penguin. I've snuck in. But I just, if you couldn't tell from my fresh face, I've only graduated university a couple of years ago, actually. So I graduated from Texas A&M University with a bachelor's degree in electrical engineering. And I'm very happy with my experience that I had there, and I think it has offered me a variety of different opportunities, one of which was getting to do an internship with Siemens, actually in Houston, which is how I then ended up being involved in a full-time program that they called a leadership development program. It was a really interesting experience. It's a rotational program by nature, so I started, moved to Atlanta, worked with a new team, control products, worked with our industrial communications and networking group, and then finally ended up working with our product lifecycle management, our software side of the business. And it's when I moved to Chicago, actually, and I think Brian has been doing a bit of evangelizing with some of you around this facility we have in Chicago called DMDII. It's a horrible acronym. The name's even longer, but it's the Digital Manufacturing and Design Innovation Institute. And it's a federally funded facility where we've had the opportunity to work with our customers, our fellow manufacturing technology providers, startups, and academia all in the same space. And that's where I was for my third rotation, actually, in that program. And of course, with the Digital Manufacturing and Design Innovation Institute, I was very involved with digitalization at the time. And that's actually where I became quite enthralled by the topic and realized that was what I had to do if I was going to stay with Siemens, is I had to be involved with what we're doing with Industry 4.0. And so I did. And I had a variety of different mentors along the way that enabled me to be able to do that and to learn the things that I was presenting to you today. And it's quite a lot to wrap your arms around if you couldn't tell. But it's a really fascinating field. And before I finish, the only thing I wanted to speak to is maybe a little bit on my own personal story with this, right? So graduating from a four-year institute with a bachelor's degree in electrical engineering, from an institution that's quite well known for engineering, right? We have a very large engineering college with 13,000 students plus when I was there. I'm sure it's more now. However, I was, frankly, just as ill-equipped to handle the realities of Industry 4.0 and manufacturing of tomorrow when I left university as many of the people that you guys were referring to earlier. And so I think rather than looking at it pessimistically, I'm very happy about my experience that I had at college. It taught me how to learn. I developed in a variety of different ways, some in the classroom, some in the bars, some elsewhere. But regardless, it enabled me to be here today, so I'm very happy with that experience. But I think what you guys are looking at here today in your manufacturing program is completely unique. And I've had the opportunity to work with our university programs, both on our hardware business and our software business. And I've had the opportunity to speak to a variety of different institutes across the United States and recruited a number of them. But what I can confidently say is what Brad was referring to earlier is completely unique to you guys. If you are capable of doing what we're pitching to our customers and the way we're approaching them to completely look at this end-to-end value chain, this digitalization, right? If you're able to educate your students in that light, even gathering 1/10 of that knowledge to give to them when they leave, either with a 2-year degree or maybe more in the future, then that will put them leagues ahead of their colleagues when they're leaving university. And I think that is a really remarkable opportunity and something that I hope that the partnership continues to grow and that Siemens will be involved with that quite extensively. But at this point, I'll stop talking. And if you guys have any questions, and I don't know how much time we have. If we don't have much, we'll be around at lunch as well. And I'm happy to answer any of those. Thank you, guys. Thanks.
So we have about 15 minutes. Any questions?
Yes.
Okay, so metal, let's say you're doing the landing gear,
Mm-hmm.
right? There's a bending point, there's a breakable point. Do you teach that computer to recognize a weak point, too big, too broken? I mean, how do you guys do that?
Yeah, so our CAD software is actually probably one of our most mature ones on our CAD and CAE style simulations. Are some of our most mature simulations. And so they're incorporating a ton of different knowledge and data points around different metals and different materials and how the behavior of those from a physics standpoint is. So I definitely was not there when those products were being developed. But what I can say is those products are very well equipped to handle bending and braking and stress and strain. With a variety of these other simulation tools too, we're able to understand heat dissipation. So for an example, we produce industrial computers. They're literally industrial PCs. They don't have any fans in them, so the entire exterior is a heat sink. Right? So we can understand, okay, if we change the design of the exterior of that box, it changes the way that product dissipates heat. We can even look into the behavior of things like that. So I don't know that I can speak effectively to how they developed those products originally. All I can say is there's a lot of data going into that material science behind it.
A lot of trust going into the computer.
Yeah.